I'm going to talk about non-right triangles, including the law of sines. Now, right triangles are nice because the Pythagorean theorem applies to right triangles. Furthermore, you always have a complementary pair of angles with right triangles. Now, there are other relations that are true for non-right triangles. They're not as nice as what we have for right triangles, but they're not too bad and they're still very useful. So one of those is the law of sines. So let me now state what the law of sines is, and then I'll show you where it comes from. So for any triangle, it doesn't have to be a right triangle. Suppose the vertices are named A, B, and C, and suppose the side opposite angle A is length A, lowercase a, and the side opposite angle B is length B, lowercase b, and then the side opposite angle C has a length C, is it lowercase c. So the law of sines says that the sine of angle A divided by the length of side A is equal to the sine of angle B divided by the length of side B. And also it's equal to the sine of angle C divided by the length of side C. Now, to see why that's true, let me draw an altitude with one endpoint at point B, vertex B. Okay, so an altitude will make a right angle with the opposite side of the triangle. And let me call the length of that altitude h. So the sine of A, angle A, is equal to, for the right triangle that includes angle A, it's equal to the length of the opposite side divided by the length of the hypotenuse, which has a length C. And the sine of angle C is equal to the length of the opposite side of the right triangle containing angle C. And that's equal to h over the hypotenuse, which has a length A. So now what I can do is I can solve for h in both equations. And now I can set the right sides of both of those expressions equal to h. I can set those equal to each other. And so I'll get C sine of A equals A sine of C. And let me divide both sides by the length of side A and the length of side C. So I get some cancellation. And so I end up with the sine of A over A equals the sine of C, angle C over side C. Now, every triangle has three altitudes you can draw from with an endpoint at each of the three vertices, right? So I could do a similar derivation to get an expression with respect to the other altitudes. And if I did that, I would get that these two expressions are also equal to the sine of angle B over the length of side B. Okay? And you can do that with the other altitudes if you like, to convince yourself that indeed those three expressions are equal. Okay? So that establishes the law of sines. Now let me show you what it's useful for. I'll do some example exercises now. Suppose I knew the following information about a non-right triangle. So I know two angle measures and I know one side length. And suppose I wanted to know the side length denoted by the variable x. Could I find that? Well, using the law of sines, I know that the sine of 35 degrees over 7 is equal to the sine of 105 degrees over x. Now I can cross multiply. And now I can divide both sides by the sine of 35 degrees. Okay, and so that expression is equal to the desired length. You can also get a approximate decimal, which is 11.8. Okay, so that was an example using the law of sines to find a side length. Here's an example of using the law of sines to find an angle measure. Suppose I knew the following information about a non-right triangle. So I know two side lengths. One of the lengths is 5.5, one is 4.7, and I know an angle measure. One of them is 63 degrees. And suppose I wanted to know the angle measure denoted by the variable alpha. Could we calculate that? And the answer is yes. We could use the law of sines. The sine of 63 degrees divided by 5.5 is equal to the sine of alpha over 4.7. Now I can isolate the sine of alpha by multiplying both sides by 4.7. And that is an expression equal to the sine of alpha. So let's take the arc sine of both sides. And that is the correct length. Now you can punch it into a calculator and get the following approximate angle measure: 49.6 degrees. All right. Let me remind you about a limitation of the arc sine function. So the range of the arc sine function does not include obtuse angles. So that can lead to some problems if you're not aware of that. Here is an example of an exercise where the arc sine would miss one of the solutions. Suppose a triangle had an angle A and B. And suppose we knew the measure of A but not the measure of B. Okay, suppose the measure of angle A was 39 degrees. And suppose angle A was opposite a side with a length of 28 meters. And suppose angle B was opposite a side with a length of 41 meters. So, can we use the law of sines to find the measure of angle B? Well, let's try it. So, the sine of 39 degrees all over 28 is equal to the sine of B over 41. So the sine of B, if I multiply both sides by 41, I get 41 times the sine of 39 degrees all over 28. And so taking the arc sine of both sides, I get that B is equal to the arc sine of 41 times the sine of 39 degrees all over 28. And that is approximately equal to 67.1 degrees. Now, that is not the only angle measure with the necessary sine value. Another possible solution is 180 degrees minus that solution. 180 degrees minus 67.1 degrees. So, in other words, 112.9 degrees. Okay? So, this question actually has two solutions. 67.1 degrees and 112.9 degrees. Try to draw triangles with those angles, and you will see that indeed it's possible to draw two different triangles that satisfy the original criteria. All right? So let me have you try a similar exercise, and you be wise about the arc sine function so that you don't miss any solutions. All right? So suppose that a triangle had angles A and B, and again, suppose we knew the measure of angle A but not the measure of angle B. And we knew the side opposite angle A, let's say it has a length 1.5 centimeters, and let's say the length opposite angle B has a length of 2 centimeters. So try to solve for possible angle measures for angle B. So pause the video and do that now, please. Okay, so I'll go ahead and solve it as well. So using the law of sines, the sine of 30 degrees over 1.5 is equal to the sine of B over 2. So the sine of B is equal to 2 times the sine of 30 degrees over 1.5. So B is equal to the arc sine of that. The arc sine of 2 times the sine of 30 degrees all over 1.5, and that is approximately equal to 42 degrees. but we also need to consider 180 degrees minus 42 degrees, which is 138 degrees. So the full solution set includes 42 degrees and 138